Okay, so I'm going to be talking today about our least invasive technology, which are complete neural stimulation and recording modes that are actually below a millimeter cubed. We've shrunk them down to the micron scale. We are actually looking to shrink them down further, as you'll see. And these modes are designed for peripheral nerve interfacing. And so I really don't need to introduce this to this audience, but peripheral nerve stimulation is a commercialized neurotechnology. This example here is from a company called Cyberonics that has commercialized a stimulator for the treatment of epilepsy. It's basically an implantable pulse generator, just like a pacemaker or a deep brain stimulator implanted in the chest cavity, and we have electrodes that are actually cuffed around the vagus nerve. Now, peripheral nerve stimulation has been shown to be efficacious in a number of clinical indications, including for control of inflammatory disease, respiratory disease, incontinence, chronic pain, and so on. So our vision, what we'd like to do is actually get rid of this huge device that you have to implant through quite an invasive surgery and move toward very, very tiny little wireless motes that we can actually implant through a laparoscopic surgery, insert through a cannula, or perhaps even inject image-guided injection directly to the site itself. And we power and communicate with these devices through ultrasound, and I'll motivate that in just a little bit. So to shrinking things down to that level is a pretty hard problem. We've actually been working on it for the greater part of a decade at UC Berkeley. And this was one of our first attempts where we tried to make little tiny neural recording motes that are shrunk down to a millimeter. We put a little antenna, and to the best of our kind of design capabilities at that time, we squeezed about 5 microwatts out of it. Obviously, we really want to shrink this down further, but we want more power, and this is a difficult problem. So one of my colleagues at UC Berkeley recognized, so Professor Michel Maharbez, he recognized that we can use ultrasound and an ultrasonic transducer, and if we beam the ultrasound directly into this implanted transducer, we can actually get quite a lot of power out of it. In fact, orders of magnitude more. And notice that it measures actually even smaller, below the millimeter scale. How is this possible? Well, first of all, ultrasound propagates extremely efficiently in tissue. It has about an order of magnitude less attenuation than RF does. It has a very high FDA intensity limit because it's safe. It doesn't absorb into tissue quite as readily. It can be unfocused or focused exactly the way that RF can, so that's a nice feature. And most importantly, the wavelengths are actually extremely small, so we can have resonant structures down at very, very small feature sizes well below a millimeter. Okay, so from that, a number of professors at Berkeley, including Michel Maharbez, Jose Carmena, Elad Alon, Jan Rabai, actually built a beautiful demonstration that they called neural dust, where they had an ultrasound transducer that is 750 microns on a side, and a single transistor to perform a little bit of neural recording. And what they demonstrated was the ability to beam ultrasound down to that device and get a reflection back that was essentially, that could be decoded into the recording of the firing of a nerve. So this was a very, very nice demonstration that was published back in 2016. Now, 2016 is when I joined the faculty at UC Berkeley. And what we wanted to look at was to take this platform of neural dust and see if we could do something a little more sophisticated with it, maybe have active circuits and perhaps not just do recording, but also do stimulation. So the first thing we looked at was building a peripheral nerve stimulator on the neural dust platform. Now, this presented all kinds of new challenges. So first of all, we want to keep the volume just as small. We really don't want to increase the size of this device substantially. We need, I showed a number a couple of slides ago that we can beam in a few hundred microwatts. We need all of that power in order to stimulate a nerve. So we need extremely efficient conversion of that incoming ultrasound to stimulation charge for the nerve. We need precise control of the charge at every phase. So that's why we need active circuits in order to control this. And we don't just want to be operating blind. We need that device to talk back and tell us, okay, I'm stimulating, everything's working properly. It's all safe here. Okay, so this is the device we ended up building, kind of jumping to the punchline. But it looks a lot like the original neural dust. It has that same piezo crystal. This time it has an active integrated circuit in order to perform stimulation. And it has a very small off-chip capacitor. That's because we need to store a lot of charge in order to transfer that charge into the nerve. The entire volume is 1.7 millimeters cubed. This is water displacement volume. And we have very efficient conversion, over 80% of that incoming power to stimulation power. Of course, precise charge control, and a little bit of bidirectional communication. For safety, I'll show you what that's about. So back to some of the challenges, how do we achieve that very, very good efficiency? That's, one of the first things we did was we made these moderately sized electrodes for the device that are actually sitting at the bottom, pressed up against the nerve. We certainly could make them bigger. They're reasonably high impedance, and we electroplated them with P.PSS in order to lower their impedance by 2 orders of magnitude. What this does is it helps us stimulate with hundreds of microamps, but without exceeding voltages that are about 2.5 volts. This is important because it allows us to put this in a standard CMOS process and have very, very efficient circuitry without having to boost up that voltage very high. The second piece of how we achieved this efficiency is that we completely designed a custom wireless protocol. This is not performing anything standard like Bluetooth or Wi-Fi. This is not a generic link. What it is it's just a wireless link that has one purpose, and that's to tell the stimulator how and when to stimulate. And so the way that it works is first we beam down the ultrasound to power up the mote. Then we turn off the ultrasound, and the amount of time that it's off sets the amplitude of stimulation. Then we send a command to stimulate, and as long as it's on, it's stimulating. So it's just the ultrasound wave that defines how long it stimulates for. Again, we shut off the ultrasound and the mote stops stimulating. And then in the next phase, it recharges the capacitor. At the same time, it has a shorting phase where it shorts the electrodes together, clears the charge away, and then repeats. And what's nice about this protocol is that, first of all, it doesn't require any memory because everything is set from the external ultrasound. It also doesn't require any timing precision. We don't actually have a clock on the chip at all because all of the precision is simply set by the edges of the incoming ultrasound. So we're really just doing edge detection. This is a very low power thing to do. And just for the circuit designers in the crowd, I'll do this very quickly. We power on the device, it charges up the capacitor, and then we ping pong back and forth between the two states of stimulate, short and recharge, stimulate, short and recharge. Okay. So we tested these devices in vitro by suspending them 5 centimeters away from the external transducer. They were suspended in ultrasound gel for this particular experiment. Here you can see it runs back and forth. We have the recharge, and then this is a stimulation pulse. We have recharge, stimulation pulse, and what you can see, the yellow is actually the voltage on the electrode itself, indicating that we've stimulated. And what you can see is that we can actually change the amplitude and the duration of each pulse, even from pulse to pulse, because it's all being controlled from the outside world. Now, what this is, one thing I actually didn't mention is that when we're stimulating, we're actually also changing the impedance that's seen at the piezo, which changes the reflection coefficient. And so what we see is a distinct decrease in the voltage across the piezo and also the received voltage. And so we can observe this change, and we know that we're in stimulation mode when that happens. And so what we receive from the outside world, this is the relative amplitude of the received signal, is we can clearly differentiate when the stimulation is off and when the stimulation is on. And we just have this kind of 1-bit safety indication, but it's enough to know that we're operating properly. We also tested these devices in vivo by cuffing them onto the sciatic nerve of an anesthetized rodent, which you can see here. Here's the circuit, the piezo, the off-chip capacitor. And what we're doing in this experiment is we've sutured up the animal. We're entirely communicating to this mote through ultrasound, and we're recording the hind leg muscle contraction, which is what the peripheral nerve, or the sciatic nerve controls. It actually kicks the hind leg back of the animal, and I'll show you a video of that in a moment. So the first thing we did was just sweep different stimulation amplitudes. What we get then is, this is the compound muscle action potential when we get, as we're activating the muscle, and when we plot the current versus the amplitude, we see these nice classic sigmoidal curves of complete recruitment of the muscle that's capable through this device. We did the same thing by varying the duration of the pulse rather than the amplitude. And here you see we have extremely fine control, and again, full recruitment of the muscle. Here is a photo of the experiment. Apologies if you're a little queasy. You can close your eyes at this point. You can see that the animal is sutured up, and I will show you a video of the stimulation. All you're going to see is that every time we stimulate, you should see the hind leg kicking. And so you'll see that here. And we'll show a couple of different angles. And we've been able to observe everything from very light kicking all the way to complete tonic contraction of the muscle. Let's see. If we have one more, yeah, this is probably the best angle. You can very clearly see the kicking. Okay. Now we've actually taped out even tinier versions of this chip that are 500 microns by 200 microns, and with a new assembly process, we can get these devices down really low. So our current device, it's not the smallest peripheral nerve stimulator ever built. There are many groups actually working on this problem, which is wonderful. But in terms of the depth that we're able to reach, so we're actually running these experiments at 5 centimeters of depth, and as well as the efficiency that we're able to reach for these volumes, we're about an order of magnitude better than the best state of the art that we're aware of. And the next generation, once we are able to shrink these down, we're actually going to be reaching 1 to 2 orders of magnitude better in these figures of merit. So now we have our stimulator, and of course we want to close the loop with a recording device. Now, the original neural dust was in fact a peripheral nerve recorder, but the focus at that time was not on strictly on performance. It was really on demonstrating the concept, showing that we can power and communicate with a device through ultrasound. And now our focus has shifted on having more of an active circuit where we can get better performance, higher input linear range, much lower noise floor, higher gains. And we want to actually be able to communicate with many motes at the same time. So let me walk you through a little bit of how neural dust works. So first, as I mentioned before, we beam ultrasound down to the mote, and we get a reflection back. So that that pulse of ultrasound takes a certain amount of time to reach the mote. The mote then modulates that ultrasound and sends it back toward the outside world, and it takes 2 complete time of flights to complete this, this task. So basically the longest beam of ultrasound that you can send is equivalent to 2 time of flights of your device. Now, if your device is far away, it's very, very deep in tissue, then you have a nice long pulse. And you can think about doing things like sending a whole bunch of bits on that pulse. Maybe you have time to send 8 bits digitally. The problem is that if your mote happens to be implanted a lot closer, and your time of flight is a lot shorter, then you don't have that kind of time. You can't send a lot of bits, and that really eats into your resolution. So what we've chosen to do is do amplitude modulated backscatter, where we actually send the amplitude of the signal encoded in that short pulse. And this gives us more information per cycle for our device. Now, digital modulation is obviously, well, frankly, easier. It's very clear to see the difference between if we short the piezo and we open the piezo by eye. You can see these are very clearly distinct waves. The problem is if we do things the way, if we just have a variable resistor, we vary the resistance in between that's shunt across the piezo, what we see is that we don't get a linear curve. It's highly nonlinear, which means when we send the amplitude modulated wave, we're going to get a lot of distortion. So what we've done is, so that where this arises really is just it's a resistive divider between the internal resistance of the piezo and the resistance that you're modulating across it. And we did a bunch of analysis, and what we showed is that it's actually rather simple. What we need to do is have a linear voltage that sits across the piezo. And if that voltage is linear, then our reflected wave is also linear. And I'll run through this very quickly, but we do this pretty simply by having a linear current that's proportional to our input voltage. And that current across the piezo generates a linear voltage. Of course, the piezo is running at AC. It's running at its resonant frequency. And so we have to upmodulate that current to the same resonant frequency as well. Okay, finally, we want to be able to interrogate more than one mote at the same time. So what we do in this case is, so each pulse now is proportional to the amplitude of the sample. And we put each of these pulses onto a unique subcarrier. So each mote would have its own unique subcarrier. This one might be running at 30 kilohertz, this one might be running at 60 kilohertz. You'll get a superposition of the 2 pulses coming back, but because they're running at unique frequencies, we can actually separate them out in the back end, what's coming from mote 1 and what's coming from mote 2. Okay, I'm not going to run through the whole chip, but of course we designed a whole chip and interrogation system to do all of these tasks. And here's the completed assembly. This was actually extremely small because we're doing a single link power and data. We just have one piezo. We have no external capacitor this time. We have a tiny chip that's 500 microns by 500 microns. And so the entire assembled volume is 0.8 millimeters cubed. So now we're down in the sub-millimeter cube regime. The entire mote takes 37 microwatts. That's well below the amount that we actually have to spend. And it has good enough noise and bandwidth to actually even do brain recording. So I'll get there right at the end. So again, we made in vitro measurements of these motes, and we sent beautiful, pristine sine waves. And what you can see is that we can actually receive pretty nice sine waves. It's nicely linear, as I mentioned before. It's the equivalent of sending about 8 bits. And we can also send neural signals across this link. We've shown pre-recorded neural signals that don't get heavily distorted. Okay, finally, we wanted to show that you can measure more than one mote at a time. And so we suspended 2 motes, each running a different frequency sine wave. We receive the complete backscatter, and we're able to demodulate the 2 sine waves. There's actually much nicer data than this in our paper that shows that we can send 2 distinct frequencies, and the rejection from the other mote is about 60 dB, which is not too bad. In the lab, we have 3 motes up and running. We're scaling this up further. Of course, we want all of these devices we want to include the stimulation in this and have a complete closed loop experiment in the future. Finally, just a little teaser for the future is that we're also interested in having these motes perform brain recording. And in the lab right now, we're working on essentially showing that we can do this through a thinned skull as well. So I want to thank my research group, but in particular, I'd like to thank my collaborators, Michelle Maharbiz and Jose Carmena, and also the students and research scientists that really drove this work forward. My student Miraj Ganbari, David Pike, who is a student in the Maharbiz and Carmena labs, and a research scientist that was formerly in my group is actually now a professor, Dr. Ben Johnson, or I should say Professor Ben Johnson, and of course our sponsors for this work. Thank you for your attention. I'd love to answer any questions you have.
Thanks, Rikky, for this very exciting presentation. It's wonderful to have this going from non-invasive modalities to actually be able to penetrate very deeply in the brain. It's quite amazing. So we have plenty of time for questions. And I'll ask that you use the microphone, so raise your hands and we can.
Let's see, you mentioned 30 kilohertz, 500 kilohertz. What sort of range of frequencies is practical with your technology?
Well, so the resonant frequency of our motes is close to 2 megahertz. The signal itself, we're sampling at about 10 kilosamples per second. And then those higher frequencies that I mentioned, the 30 or 60 kilohertz, those were the subcarrier frequencies that are unique to each mote. And so, there is a limit to which we can scale those. We have a whole analysis in our paper that shows that we can, with our current motes and our current setup, we can scale to about 8 to 10 motes. And then we run out of bandwidth.
That's what I was getting at, thanks.
Yeah.
Very nice talk. Have you thought of using sort of a wavefront shaping to focus ultrasound energy you can provide a guide star to focus to the point you want?
Excellent question. Absolutely. We are, in fact, making those measurements now in labs. So we have an arrayed external transducer, and we are working on beam forming toward motes, even multiple motes at a time.
So I have a question too. So I noticed that you use a monophasic simulation.
Yes.
Yes. Can you say a bit more? But typically, one would use biphasic or triphasic.
Yeah. So this is an excellent question. So we wanted to keep the mote simple. So we are using monophasic. We don't let the charge accumulate. We do short the electrodes together to clear the charge. There is some reverse rush current, and we have in the paper that's going to be coming out in a couple of months. We have it's actually on arXiv, so if you'd like to take a look, we have an analysis that shows that our reverse rush current is well within safety limits. That said, we certainly could modify the design to do biphasic as well. Thank you for the question.
One more question.
So Rikky, thanks for the talk. Can you comment on the requirements for the transducer for the external device, and also to what extent this would be scalable to milliamp level currents that are currently used in VNS?
Yeah, that's an excellent question. Thanks for the question. So I showed at the very beginning a number that said 350 microwatts is what we can send into our device. That's using really kind of the simplest single element external transducer. And at the maximum rate that we can hit it, so the maximum amplitude that we can hit that transducer, we can couple 350 microwatts. That's not limited by safety, that's limited by how hard we can hit the external transducer. Now, with a better transducer or a transducer array, we can scale that up to milliwatts.
We have time for one more question.
Very nice presentation. After the stimulation is done, so how do you remove those dust, those transducer devices? Or do you have to remove them at all? Thank you.
Yeah, so the question is how we explant. So first of all, you don't necessarily have to remove them. So you certainly can leave them in there. However, they're cuffed to the nerve. What people have shown, we've only done acute studies. We haven't done long-term studies. What people have shown is that there is some nerve growth around the cuff where it can be difficult to explant, but that is something that we're working on. There could be materials that you use where it's significantly easier to explant the mote.
Okay, let's thank Rikky again.